All right, folks, we're going to hit the last of the pages here, last 5 pages of notes here, and this in this video. So flow rate. Flow rate is how much fluid volume passes a point in a conduit. Now, your students may not be familiar with the word conduit. Of course, that means something that carries the water, right? Okay, so that could be a pipe or it could be a river or something like that. Every second. Now, there's no well-defined symbol for flow rate. The symbol that I personally use is capital 5 for flow or whatever kind of thing. The units are volume every second, so that'd be cubic meters per second. Okay, and two basic equations. Flow rate is delta volume over delta time, but flow rate is also the area, cross-sectional area of the fluid times the velocity of the fluid, the flow speed, right? So I'm going to label this the cross-sectional area, and V is the flow speed, okay? So here's the story on why it's the same. These two give me flow rate. The reason why they give me flow rate is this. Let's say that you have a pipe of some kind. The area, cross-sectional area of the pipe is A. All right. Now, this cylinder of fluid, delta V, is going to pass by this arrow in a time delta T. This delta V is going to pass by in a time delta T. So in time delta T, we're going to go from here to here, right? We're going to go from here to here, right? Well, what is delta volume? Delta volume is area times delta this distance, which I'm going to call x, delta x. Okay, so area delta x, right? The area of the base times the height. That's where that volume equation comes from. So if I say delta volume over delta time, that would be area delta x over delta time, which is area times velocity. You guessed it, right? Okay. Now, here's the deal. The deal is that you can't just make fluid appear out of nowhere, and fluid cannot disappear either. So the principle of continuity says this. It says the total, or I'm going to say the flow rate at all points in a conduit is the same, and that is, and I'm going to say this, unless there is a junction, okay? And here's what a junction looks like, okay? A junction looks like this. If you have like flowing in, and then there's like a T where there's some flowing out, but then there's also some flowing out that way, right? Flowing out and flowing out. In this case, the total flow rate in equals the total flow rate out if there's a junction. Now, if there's no junction, then if you have a big area pipe and it tapers down to a small area pipe, then this cylinder right here might turn into this cylinder right here. That's the same volume. So this fluid passes that point in the same time that this same volume passes that point. That means that it has to go faster. The fluid speeds up when it goes into a smaller conduit. And so that's the continuity equation. The continuity equation says area 1, velocity 1. This is the flow rate at point 1 in the pipe equals area 2, velocity 2. That's flow rate at point 2 in the pipe. So maybe this is point 1 and this is point 2. So the continuity equation chooses 2 points in the fluid to compare. You're going to find out later that Bernoullis does the same thing. As this 1 on one side of the equation, point 2 is on the other side of the equation. Okay, so in other words, if the area of the pipe tapers down to a smaller area, the fluid flows faster, right? Okay, so area 1, velocity 1 equals area 2, velocity 2, like that, you see? With the bigger area, slower speed, smaller area, faster speed, right? And this is just conservation mass. This is just a conservation of mass, or you can call it conservation of matter. Some teachers call it that. Oh, I'm off the page. I'm so sorry. Okay, so conservation mass or conservation matter. That's what's going on. Sorry, I actually have the camera behind me for this video. You're going to see why in a moment, because I have to actually stage a demonstration out there in my classroom. So normally I'd be looking on my screen here, and it's just not working. This is super not ergonomic, right? The OSHA is going to take issue with my setup here. Okay, when a person puts their finger over the end of the hose, the water in the hose sprays faster. So the finger over the hose reduces the area the water flows out of, okay? But the flow rate, which is area times the velocity of the flow, is the same. So if there's less area, the velocity is faster, okay? And then, okay, so when the river is shallow, right? Okay, so here's what a deep river looks like. That's a cross-section, so there's a big cross-sectional area. And then a shallow river is going to look kind of like that, okay? And it has a small area. So then with a deep river, the river flows very slow, but with a shallow river, the river flows fast, and that's what makes the rapids, right? So when the river is shallow, right, that's less cross-sectional area, right? So that means more flow speed to keep the flow rate the same at all points, right? Now, sorry, the flow rate of a river does actually increase, but the only way that the flow rate can increase is for the river to have tributaries like creeks and streams flowing into it. And then this rule applies, right? Where the opposite of this is true. If you have, for example, a river, okay, has a certain flow rate 1, and then here's a stream with flow rate number 2, and then here's another stream with flow rate number 3, then this now has to have a flow rate equal to flow rate 1 plus flow rate 2 plus flow rate 3, because the water doesn't just disappear. It has to all add up. All right. Okay, some examples. The area of a typical kitchen or bathroom faucet has an area. Okay, so that's a typo because that's redundant, much redundant, right? Okay. Students really struggle with this because there's no mantissa in front. They see 10 to the negative 3 and they'll put 10e negative 3 in their calculator, which is wrong. This is not 10 times 10 to the negative 3. This is 1 times 10 to the negative 3. So this is an opportunity to teach them to watch out about scientific notation that lacks its significand. That's the numbers out in front. It's called the significand because it holds the significant figures. In computer science, it was called the mantissa. Okay, sounds like a wild animal, doesn't it? Okay, in the United States, the flow rate from such a faucet is limited to this by law. Calculate the speed that the water emerges from the faucet. So flow rate equals area times velocity. The flow rate is 1.388 10 to the negative 4. The area is 1 times 10 to the negative 3, right? Okay, so then I'm just going to grab my nifty spifty calculator here, and I'm going to do 1.388 e negative 4 over 1 e negative 3, and that's basically a flow speed of 0.14, let's say, centimeters per second, right? Okay, and then how much time would it take to fill a gallon? Well, the flow rate is delta volume over delta time, so that means that delta time is flow rate, volume over flow rate. So what's that going to be? It's going to be 3.785 10 to the negative 3 divided by a flow rate 1.388 10 to the negative 4. So then I'm sure you've already taught your students how to do scientific notation on the calculator during your unit on universal gravitation, but this is a good opportunity to review students on properly putting scientific notation into the calculator. About 27 seconds. 7.3 seconds. Okay, try it at home and see if it takes about 27 seconds to fill up a gallon of jug of milk or something might be empty. Okay, so this height is 6 centimeters. This width or whatever is 8 centimeters. This width is 4 centimeters. This height is 2 centimeters. And we're hearing that the speed in the wide section is 3 meters per second. So you can say area wide times velocity wide equals area narrow times velocity narrow. Now, you can call it 1 and 2 if you want, but anytime I have 1 and 2 subscripts, I try to replace them with something meaningful in the problem. So when I do momentum, I'll teach my students M1, V1, M2, V2, M1, V1, M2, V2, right? But then when they actually use the carts, the red and blue Pasco carts, then I'll say M red, V red initial plus M blue, V blue initial. Like I'll give them different subscripts, make them have actual meaning. You know what I mean? Okay, so the area of the wide section is 6 by 8, and the speed in the wide section is 3. The area in the narrow section is 4 by 2. The speed of the narrow section is what I want to know. Well, Frensley, aren't you supposed to convert to meters? This is a good opportunity to teach your students that if you have a proportion or an inverse proportion, then you don't have to convert units because centimeters and centimeters and centimeters and centimeters will just cancel out. This is called an inverse proportion. Inverse proportions have a pattern. A1, B1 equals A2, B2, and you can use any units you want as long as the units match. Direct proportion is A1 over B1 equals A2 over B2, like Pascal's principle, force over area equals force over area. And again, as long as these two are matching units, then it works out, right? Okay, so this is 8, so I divide. The V in the narrow section is 18 meters per second. Notice that I give the students pretty numbers sometimes in order to help them understand the physics better. When the numbers are pretty integers or the decimals, like 1 or 2 decimal places it terminates, students learn the physics better. But I also want to give examples that involve like real life applications. And when I say real life, I mean things that students deal with in their ordinary lives, right? Okay. Water flows through a pipe, has a variable diameter shown. The diameter of the pipe is 3 centimeters. Here, the diameter of the pipe is 6 centimeters. This flow is 100 meters per second. So area X, velocity X equals area Y, velocity Y, right? Okay, so what are you going to plug in for area? I'm going to plug in 3 squared, and the velocity was 100. What are you going to plug in for area? I'm going to plug in 6 squared, Vy. Well, Frensley, don't you have to convert to a radius by dividing by 2? Don't you have to convert to meters? Don't you have to put pi? All that stuff cancels out. So tell your students that if you have an inverse proportion or a direct proportion, then area is just length squared, as long as the area is the area of similar shapes. All circles are similar to each other, right? These were not similar, by the way. If you look carefully, I do not think they were similar. No, 8 to 6 is not a 4 to 2 ratio. So I actually had to plug in the areas using width by height. I didn't have to convert to centimeters to meters because that conversion would cancel out on both sides anyway. And then, well, Frensley, you just put in diameter squared. Yes, I got a diameter squared, diameter squared. The pi's would cancel out. The conversion to radius would cancel out. The conversion to meters would cancel out. That is a waste of your time. So that's the whole point of that first page, geometric scaling, is to get the students to swallow this pill. Okay, this is 900 equals 36 Vy. Or you know what you can just say? You can just say that this is 4 times the area. No, I'm sorry. This is 4 times the area. So that's got to be 1/4 the velocity. 4 times the area, double the diameter or double any length, 4 times the area, 1/4 the velocity. So velocity is 25 meters per second, right? Get your students to think proportionally that way, okay? And then same story here. Water flows through a large pipe of radius r, speed v. The pipe splits into 2 smaller pipes, have a radius of 1/4 r. So here's the r, and here's the pipe, and then here's 1/4 r, and then this is 1/4 r, right? Okay, so here's what I'm going to say. I'm going to call this 1 and 2 and 3. So area 1 velocity 1 equals area 2 velocity 2 plus area 3 velocity 3. Sorry, velocity 3. That's because this splits at this junction. So the total flow rate in has to equal the total flow rate out. Now the good news is that these are identical. So because they're identical, I can assume that these are just like terms. So I'm just going to call this area 1 velocity 1 equals 2 because these are like terms. Area 2 velocity 2 because they're equal anyway. Now, what am I going to put in for area? Radius squared. What about pi r squared? No, not pi, because it's going to cancel out anyway. Okay, V1 is just called V. This is 2. This is going to be 1/4 of r all squared. If I had pi, it would cancel out, so I'm not going to put the pi to waste my freaking time. Okay, and then the V, I'm going to call it V small, actually, if you don't mind at this point. Okay, so this is 1/16 times 2. 1/16 because of squared times 2. So r squared V equals 1/8 of an r squared V small. So now the r's are going to cancel out. The r squareds and the 8 comes up. The V small is going to be 8 times the V. So that's called variational or proportional reasoning. It's a proportional reasoning problem. You got to exercise your students on that. Okay, so Bernoullis' principle is about flowing fluids. The faster a fluid flows, the lower the pressure it exerts. So what do I want you to do? Well, first of all, what I want you to do, I'm going to bring this over here where you can see me. Okay. Hello, you can see my... Okay, so you weren't even seeing that a second ago. When I was pointing up at the screen, I said my camera's up here on the screen behind me. Okay, so now you see why the paper was off the whole time, right? So the paper was off because I have it behind me because I need to be able to frame myself here in a second, right? I'm going to frame myself for murder. No, I'm going to frame myself for a demonstration I'm doing. And I'm sorry this is all tilted. I know it looks like the movie The Third Man or Battlefield Earth with the Dutch angles, right? Both of them made me sick. Okay, so these demos, add to these demos if you, I'm looking in the camera now, add to these demos if you can think of some other better ones or find some YouTube. Look up Bernoullis' principle demos. They're all really, really good stuff. This one's a classic, although I have been told that this is not actually Bernoullis' principle. I'm going to show it to you anyway because it looks good enough for me. Okay, come on, get off of there. So you take just a strip of paper right here. I'm going to take a strip of paper, and then you blow, not underneath it, let me frame myself here, but above it. You blow over the top. And that's just a strip of paper. You can just cut like, 30 or 40 or however many students you have strips of paper and have students do it on their own, right? Okay, I'm going to shrink that down a little bit more. All right, so the idea is that the air exerts low pressure on the top. This is moving fast air here, but this is slow, or you could just say stagnant air here, which exerts more pressure. So the slow air underneath pushes up more than the fast air over the top. So again, I've been told by some teachers that this is a different principle than Bernoulli. Not going to lie to you, it works for me, so I'm fine with it. I don't feel bad about it. Now, this is the soda can demo. You can get a couple of soda cans and kind of tie them to strings. Come on, get off of there so people can see this. Okay, so let's see if I can show you this. So I'm holding the 2 soda cans by their strings. I just connected the strings to the little pop tops there, okay? And now I'm going to hold them apart from each other, and I'm going to blow in between them. You see how they come together? Watch it again. So you see how that works. Oh my gosh, the lights are going off because I'm not moving around enough. Okay, so anyway, you can see how professionally I dress for my job here. All right, so the point of the cans then is to say this, is that the still air and the still air on the sides push in a lot, but the fast air here pushes this way not very much. So the still air on the sides push inward on the cans more than the fast air going between the cans, right? Okay, so that is that's a demonstration of Bernoullis' principle. Okay, this is a really cool demonstration if you can make it work. I know a teacher who made this work using a vacuum cleaner that could be reversed. It was an old-fashioned vacuum cleaner that could be reversed, where you would take the hose and then you could blow with the hose. I'm going to do this with an electric leaf blower. I should not have to explain to you why you're not going to use a gas leaf blower in your classroom, which is an enclosed space, and gasoline, which creates carbon monoxide. I really should not have to tell you this, okay? But I am going to show you with this electric leaf blower. I will tell you, I bought this at a garage sale. I bought it 20 years ago, or no, 10 years ago. I'm not that old. 10 years ago for $20. So I don't know if you can find a leaf blower like this for $20. It would be a very, very good buy if you could get it. And then this is a rubber ball from Walmart. You know, the big bin at Walmart is a stupid rubber ball, right? And it's not even fully inflated. It's a little bit flat. You can tell, but it doesn't matter. It has to have a little bit of air in it. And then what you're going to do is you're going to turn on the leaf blower and hold. I hope you're seeing. I'm holding it right here, the ball right in front of the leaf blower, not to block it. And then I'm going to turn on the leaf blower. I'm going to let go. You will not be able to hear me because of the loud sound. So I think that's a pretty neat demonstration. It's actually the demonstration I do in order to recruit students to take AP Physics. I'll go to their chemistry classes and I'll say, hey, here's like a couple of demos. I do one where I drop a golf ball and a bowling ball with the golf ball right on top of the bowling ball, and the golf ball bounces all over the place, and that's momentum. And then I'll do one where I'll do this demonstration right here. So the idea is that this air is going slower, this air is going faster. So the faster air over the top exerts lower pressure. The slower air under the bottom exerts higher pressure. Okay, excuse me while I adjust my camera, trying to not give you a headache with my tiltiness here, right? So the air over the top goes fast, okay? So it exerts less downward pressure, all right? And then the air under goes slower, so it exerts greater pressure up. And that balances the gravity force that would bring the ball down. One of the things I want you to notice about the demo I just did is the fact that I could actually steer the ball around. When I slowly moved the stream of the air, the ball wanted to go into the stream. Here's a quick reason why you saw that. Because if I move the hose from here to here, then this is where the fast air was, exerting lower pressure on the ball. This is a top-down view, by the way. This is as seen from the ceiling. But then the air over here is still, so it exerts, and it brings the ball back into the stream. So this is an actual equilibrium kind of situation for the ball. The ball actually wants to stay in the stream because of that. Okay. If you don't do any other demo, you have to do this one. This is a really good one right here. So what you do is you give the students a funnel or whatever, and you have to be careful because you probably have to have some disinfectant nearby. I use Clorox wipes or whatever. And so you say, okay, here's the ball. Here's the funnel. You have to hold the funnel by the brim and like make up a bunch of rules to make it sound like it's an official game or whatever. You cannot, this has to be horizontal, so you can't tilt it or anything like that. And you have to, with your breath, blow the ball out. You have to blow the ball out. Are y'all seeing this here? Okay, so it's flat here. And so you'll have students who do this like that, right? Okay. This is where the disinfectant comes in. You have to disinfect after each person puts their mouth on. It's never going to happen, okay? So then, here's what you do, is you take the leaf blower now, if you have it, and now you have the leaf blower, and you turn it on and find out that the leaf blower, you can actually hear the ball rattling around in there. You can't get it out with the leaf blower. Sorry, I keep looking back, so I'm making sure you can see what I'm talking about. In fact, watch this. I'm going to turn the leaf blower on, and then I'm going to turn the funnel and the leaf blower both upside down. This shocks students. blew my graded papers all over the place. All right, well, whatever. Okay, so the ball not only doesn't blow out, it won't even, it stays in. Even when I tilt it upside down, the ball is stuck in there. It didn't fall out until I turned the air off. Here's why. Because this is fast air. And why is it? Because this is a small, let me make sure you can see this. This is a small area right here. This is a small area. So the air goes past the ball very fast since the area is tiny. Okay, well, what do we know about fast air? Fast air exerts low pressure. So the air on the top, the still air on the top pushes down harder than the fast air underneath pushes up. So when I turn the funnel over, it looks like this, and the air underneath is actually holding the ball in until this flow stops. Then this pressure balances that pressure, and the ball can fall because of gravity. So what's the right answer? Okay, here it is. I told you have to keep the funnel horizontal. You have to keep the funnel horizontal. Okay, so how do you blow and get the ball up? That's how you do it. Did you see that? Because I ain't doing it again. I have to go get the ball rolled across my classroom. You blow across the top. That's the fast air. You don't need to be seeing my ugly mug now. So let me shrink this sucker down now. Okay, so we're going to shrink you down. Okay, so you don't have to see me. Okay, so that's a fast air right there. Okay, so you have the fast air here. So that exerts low pressure. And then the slow air on the sides exerts higher pressure, and the ball goes up and out. All right, so blow over the top. So the air pushing down has low pressure, and the air underneath, which is not moving, pushes up with high pressure. So this is a great day. And I would not take a whole day on these demos, but between these demos and maybe the flow rate, I would take a day on just quickly doing flow rate and then showing these demos, having your students do them themselves. All right, here's Bernoullis' equation. All right, so we have to choose 0.1 in the fluid. Okay, oops, there's no E. This is not French. And then there's 0.2 in the fluid. Okay, and so it's going to look something like this. The pressure at 0.1 plus the density of the fluid, gravity, the height of 0.1, where going up is positive. So this is not the same as pressure at depth, right? Okay. And then plus, let's make sure you're seeing that, 1/2 density, velocity 1 squared, the speed of the fluid at 0.1 equals pressure 2 plus rho g height 2 plus 1/2 density velocity 2 squared. It's the longest equation in all of AP Physics, and that includes P2 because it came over from P2 and the C courses. It's the longest of all the equations that students will ever see in high school. Now, it looks scary, but you're going to see on the next page with our examples that it's actually not that frightening. And the reason it's not that frightening is because the student's job is to find terms that are zero. All right. Same goes for like conservation momentum. Find terms that are zero, right? Okay, this is actually a statement of conservation of energy, right? It's the energy internal to the water or fluid plus mg height plus 1/2 mv squared equals the same thing on the other side. But then what you do is you divide by volume, divide by volume, divide by volume. Mass over volume is density, and energy over volume is actually pressure. Turns out that's one of the things pressure actually communicates. It's not just force per area, but it's what's like an energy density. How packed in to volume are the joules of internal energy of the internal interactions of the air or water or fluid molecules. So that's where that comes from. Okay, so 3 examples here. A large tank contains water with a density. The height of the water is 25, so I'm going to mark that right here, 25 meters. The small plug, height equals 5 meters. Above the ground stops the drain for the water. I am going to mention to you, the reason why I don't actually put the numbers in the diagram is because if you want, you can copy this onto a different document, change the numbers, and make like a quiz or an assessment out of it. That's part of the reason why I don't put the numbers in the diagrams anywhere. You haven't seen that ever happen, is because then you can make an assessment out of things, right? Okay, I should have mentioned that before, but it just occurred to me. Okay, the cross-sectional area of the drain plug is 0.01 meters squared. Calculate the force that the water only, that means gauge pressure, from a gauge pressure. All right, pressure exerts on the drain plug before it breaks loose. Okay, so gauge pressure is density, gravity. I'm going to actually spell out the word here, depth, because the H's are already used right now. Okay, and so the density is 1,000. Gravity, I'm going to use 10 because that's an easy number. The actual depth below the top of the water, the depth is actually 20 meters. And so you get 200,000 pascals. Now, it turns out that in a moment, I'm going to call the top of the water 0.1, and this point right here is going to be 0.2 for the sake of Bernoullis. So you could have actually gotten this if you had said the following. If you had said pressure 1 plus rho g height 1 plus 1/2 rho v1 squared equals pressure 2 plus rho g height 2 plus 1/2 rho v2 squared. Well, nobody's moving, right? Nobody's moving. In gauge pressure, the air, which is what's pushing on right here. No. This is what I want, is that pressure. The air pressure is 0 because it's gauge pressure. And then these two heights are 25 and 5, which if you subtract, you get the 20, right? Okay, so that, and then how am I going to get force? Force equals pressure times area. So that's 200,000 times 0.01, which is 2,000 newtons, I believe. Okay, sorry, there's not a lot of space. You have a Word document version of this. You can space it out even more if you'd like. The speed of the water as it emerges from the drain. Okay, so again, I'm using this equation. Pressure 1 plus rho g height 1, which is really the capital H. That's the height up to 0.1. Plus 1/2 rho v1 squared equals pressure 2 plus rho g, the height number 2, which is little h, plus 1/2 rho v2 squared. V2 is what I want, the speed that the water comes out. Okay, once the plug is gone, this water is touching the air and that water is touching the air. If you choose a point where the water directly touches air, then that point has air pressure. So this is atmosphere and atmosphere, so that subtracts away. P1 equals P2 because both points touch the air. Okay, I'm going to say this. I'm going to say that V1 is very close to 0. Why is V1 very close to 0? Because this is a very big area, because the area is big, and we just learned from continuity that if the area is big, then the velocity is slow. How much bigger does the area need to be? It turns out to make this term like 1% as much as this term, like 1% or less, you just need to have like a radius that's 3 times bigger than the radius of the hole. It's not even that much, okay? So when I show you the soda bottle in the next video, soda bottle has a 1/4-inch hole in it, and the soda bottle itself is like 4 inches across. I mean, this term will be less than 1/10,000th of a percent of that term, so you can just call it 0. Okay, now this term is basically 0. If I bring this over, then you can factor out h minus little h equals 1/2 rho v squared. This is the v coming out. The densities cancel, and this just becomes 2g delta h equals v squared, which you'll notice is actually, the same result that you would get if you were to have like a cart, and the cart starts at 25 meters high and it ends at 5 meters high and there's no friction, right? It'd be the same result. It'd be v equals the square root of 2g delta height after doing conservation of energy. So fluids, this is just a review of conservation of energy. Okay, 2 times 10 is 20 times another 20 is 400. The square of that is 20 meters per second. Okay, the volume flow rate is area times velocity. 0.01 is the area, 20 meters per second. So you get 0.2, I believe, cubic meters per second, which is a huge amount, actually. That's actually like 2 bathtubs full of water every second. I'm not even kidding you. Small bathtub, right? Like a small, if you have a big master bath, it'd be 3 of those every second. Holy smokes. Okay. The syringe has a plunger, a barrel, which is way bigger in area, than a little needle. The needle has an area of 6 times 10 to the negative 4 meters squared, right? Okay. The syringe is filled with water, and a force of 120 newtons is exerted on the plunger, which is, oh, no, I'm sorry, the barrel. The barrel has a cross-sectional area of 6 times 10 to the negative 4 meters squared, and the needle has a much tinier area than that, probably 10 to the negative 6, so less than 100th as much as the barrel area. Okay, the gauge. All right, sorry for that little interruption. We had a camera glitch, so there's a jump cut probably. Okay, so the pressure is only the force applied, not counting the air. And the reason I want gauge pressure is because the air is pushing on both the needle and the plunger. So the air pressure on one side and the air pressure on the other actually cancel out. But the pressure applied by the force of 120 newtons over the area, 120 newtons over 6 times 10 to the negative 4, that is not canceled out by anything on the other side. So I do 120 divided by 6e negative 4, and that is a pressure of 200,000 pascals. Okay. Now, how fast does the water emerge from the needle? I'm not going to use 1 and 2 this time. I'm going to use B for barrel and N for needle. Pressure in the barrel plus density, gravity, height of the barrel, plus 1/2 density, velocity of the barrel squared equals pressure at the needle plus density, gravity, height at the needle plus 1/2 density, velocity squared at the needle. Okay, now the pressure at the needle, because we're using gauge pressure, is going to be, the pressure at the needle is 0 because it's touching air, and we're using gauge pressure, right? Now, if we were using absolute pressure, then this would be 100,000, but then this would be 300,000 because we'd have to include air pressure there also. So 300,000 and 100,000, or just 0 and 200,000, right? Okay. The heights are the same. Heights are the same. We're holding the syringe sideways, and even if we were holding it vertically, the difference in height would be a tiny term, it turns out. So then that eliminates this, and then the speed in the barrel is basically 0 because the barrel has more than, I mean, if the area of the barrel is 10 or more times bigger than this term, than the needle, then this term is 1% or less of that term. So basically, we're just going to argue that that's worthless. So you just get the pressure in the barrel equals 1/2 density, the velocity at the needle squared. So 200,000 is going to equal 1/2 times 1,000 density times v squared. And so you're going to get a speed of like 20 meters per second out of that, right? Okay. Now here we have a hose, and we have the height of the nozzle, okay? Carries water, leads to a nozzle that's elevated above the ground. The nozzle has a diameter D, and the hose has a diameter 3D. So here's what I know based on that. I'm just going to tell it to you right now. You know, if you do area hose, velocity hose equals area nozzle, velocity nozzle, then what I know is that the area of the hose is 9 times bigger than the area of the nozzle. Why 9 times the area? Because 3 times the diameter. This speed is 0.2, so then this is going to be V at the nozzle of 1.8 meters per second. So again, this is that geometric reasoning I want students to be able to do, and quickly. It's because if it appears on the multiple choice, and they can do it really fast. All right, what's the pressure of the water in the hose at the ground level? All right, so pressure of the hose plus rho g height of the hose plus 1/2 rho velocity of the hose squared equals pressure at the needle nozzle nozzle. Never mind. Okay, so There you go. There. That was not racial slurs I was making fun of. I think Laverne and Shirley. It's just a show I saw once. Okay, so there you go. All right, please don't report me. The pressure at the nozzle is 0 because you're touching air, okay, and we're using gauge pressure. So the air pressure and gauge pressure is 0. So let's cancel that out. The height of the hose is 0. The height of the hose is 0 because basically on the ground. And this is what I'm solving for right there. So let's have a look. The pressure at the hose plus 1/2 the density 1,000 times the speed in the hose is 0.2 squared. Okay. And then over here, we get density 1,000, gravity 10, and the height here is 0.3 meters. 0.3 meters. That's rho g height. And then 1/2 rho, and then the velocity at the nozzle is 1.8. 1.8 squared. Now, I am going to actually calculate each of these out, and I have an educational point to make to you and that you can make to your students. This number is 20, pressure hose plus 20. All right, this number is going to be 3,000, and then this number is going to be 1/2 times 1,000 times 1.8 squared, okay? And then we get 1620 right there. Now, again, get this and get it good. The hose had a diameter only 3 times bigger than the nozzle. 3 times the diameter, and look at what that does. 162 over 20 over 20. Okay, this term is 81 times bigger. Or more to the point, this term is about 1% as big. So that's the argument I keep making up here where I say, oh, the speed in the barrel is small. The speed in the big tank is small. Because with just a diameter ratio of 3-to-1, this is now a little over 1% as big as that. So what if the diameter ratio was 100 times the diameter to 1? Then this would be, I don't even know, like less than a billionth as much as this term, 0. Now, today I'm not going to make it 0, but you get the idea. So I subtract, and if I subtract, I get the pressure of the hose is 46 pascals. Again, in gauge pressure. If it was atmospheric, it was absolute pressure, there'd be a 1-0 in front of that for the 100,000 of atmospheric pressure. Okay, so last video, lots of Bernoulli-related labs and activities. So I hope you'll join me there, and I hope I won't have a camera problem. I'm going to fix my power settings so that the camera doesn't bug out on me. All right, I will see you there.